So this is joint work with Fabrizio Dell'Acqua, who is a PhD student and is here today in the back. And the topic of our presentation, of our paper, is bias in AI. Okay, so you've probably seen lots written about biased AI in the last couple of years. There is a somewhat famous ProPublica article that purports to find bias in the way bail is being set in certain bail setting algorithms. There's also a famous book by Cathy O'Neill that purports to document all sorts of different kind of examples of biased AI. Okay? But one thing that doesn't get talked about as much, I don't think, is first of all, what caused these problems to arise to begin with? And second, what are we supposed to do about it? If you're a policymaker or a CEO and you want programmers to not develop these, then what should you do? So our paper presents data about the effectiveness of different policy interventions, and the data comes from a field experiment in the AI engineering and development process. So in just to give you a preview of the design of this experiment, we have 300 AI software engineers who are all tasked with the same problem, which is to predict the scores on a standardized math test as a function of biographical covariates of the people taking this. We have rich covariates not only about the test takers of math, but also about the 300 different AI programmers. So we can examine how different covariates are correlated with the different performance of these different outcomes. And we also have 4 different experimental interventions to try to measure what's the causal effect of different policies on the algorithms that are being produced. Okay? And so as outcomes, we not only have the performance of the predictions coming out, of these algorithms coming out in the form of about 2,000 predictions per algorithm. All right. So we not only have the performance of the algorithms on the actual prediction problem, but also how the different programmers approached the problem. We can get at that by examining their code, and they answered a survey at the end of the task to see how exactly did they approach it technologically, and they're thinking about the social science insofar as they did. Okay, so just jumping right in. So why did we study math? Well, math is one thing where there are objectively right answers that we can verify. In addition, math is the topic of gender stereotypes that could plausibly lead to algorithmic bias coming from lots of different sources. So talking for a moment about our experimental treatments and the hypotheses behind them, the first one we're looking at is broadly so-called biased programmers. So the people that think that biased programmers are the problem behind algorithmic bias essentially say that we have a workforce diversity problem, and that's why we see biased algorithms. Okay, so basically there are too many mostly white male well-educated men who are creating these algorithms, and they may not be deliberately biasing the algorithm. They may just go about engineering in a way that's unconsciously or subtly informed by their own life experience and perspective. Since Ajay mentioned the conference volume, I did want to say, in Catherine's chapter in the Future Research Agenda, they talk about the need for trying to get data on this question, which comes up a lot in policymaking. The implications for the biased programmers hypothesis is that we need to improve representation of the AI workforce. That will lead to more socially conscious code being written. And also the implication is that we should try to de-bias engineers by making them more aware of this issue. Okay? So in our field experiment, we examined this hypothesis first by recruiting a relatively diverse set of subjects. There were about 30% women. This is, doesn't sound like a lot, but it's actually more than typically are in AI jobs. Also, at the end of their prediction tasks, we ask everyone to take the implicit association test to try to measure whether or not whatever implicit biases appear in that test were sort of passed along into the code that they write. And then finally, we have an experimental intervention, which is a non-technical bias reminder that's randomly assigned to some of the subjects, that says, don't forget about algorithmic bias. If you use data in a naive way, or if you engineer without thinking about this, you might produce something that has a social consequence. Okay. The other major hypothesis that we study is this biased data. And this basically says that it's really data and engineering processes that are the problem, and that we have biased data coming from the world that will get baked into the algorithms unless it's accounted for somehow. So there are lots of versions of this critique, but the typical whipping boy is convenience samples and how companies use data that they conveniently have access to without thinking about their representativeness of this. Okay, so this was also mentioned in Matt's kind of chapter in the conference volume for a couple of years ago as well. And the policy implications, I think, are different than biased programmers. The implications that we need to improve the data pipeline and also teach technical methods to kind of pull the bias out of the data. So in the last couple of years, there's been an explosion in computer science of new methods in the fair machine learning space to try to make algorithms new fair. And so these people think we should just use these. Okay? Now, in our experiment, we have a better training data intervention. Basically, some people get a convenience sample. So this is the math scores of people who are currently employed in jobs where they do lots of math. So this is like what a company would have easy access to if they were hiring in this field. And then other people randomly receive a properly weighted sample of the test population. Basically of the broader society. And then in addition, we also have a technical training intervention that gives the programmers a jargon-free 3-page white paper explaining how to implement one of these fair machine learning techniques to try to debias through better technical methods. So just to tell you a little bit more about the training data before I get to the results, this came from the OECD's PIAC survey. We did not tell them it was from this government data set. We told them that we were a company trying to build a hiring algorithm, and this was to try to blind them from the underlying research hypotheses. And everyone was given the same test data, which was a random sample of the population as a whole. So to summarize the design, we have 3 groups that get a convenience sample. One's a control group with no help. One gets a non-technical reminder. One gets a reminder with some technical advice. And then the final gets good training data or a perfectly representative training data. Okay? So let me get into some results. Here is a 2D kernel density plot of predicted math performance versus actual math performance. And luckily, this is somewhat upward sloping, but as you can see, the predictions are kind of all over the map. So all of these programmers, sorry, not all of them, but over 70% were enrolled or were graduating from an elite engineering school. In addition, a lot of them either already had jobs or had worked at well-known kind of top tech companies like Facebook or Google. So I don't think it was just the case that they were bad programmers. There are a few other papers that try to ask relatively quantitative people, scientists, academics, machine learning people, to all predict the same thing, and this is pretty common. They do a little bit better if you ask them to predict or if you evaluate their rank orders as opposed to the raw test scores. When we look at the questions of bias, which are the sort of motivating questions, issue behind this paper, if you perform a Becker-style test, that is, look at the true math performance conditional on the predictions, it looks like the algorithms are actually biased against men as a whole, which is not, what the sort of rhetoric says about the problems with these convenience samples, but you can, I think, justify that theoretically without too much difficulty. On the other hand, if you look at predicted math performance conditional on actual performance, which is a metric of bias that lots of policymakers care about and that comes up a lot in this computer science literature, the algorithms are actually biased against women. And these two metrics move in opposite directions with the treatments and the covariates. So at least in this case, it almost suggests that policymakers would have to choose one of these to prioritize if they were thinking about how to interpret this experiment. Okay. So just summarizing across a wide variety of measures, here's how our interventions worked out from best to worst. Okay, so you may not be surprised. There's nothing quite like having better data. This improves performance by 0.2 standard deviations on on kind of lots of different metrics of performance. The second best thing, which is 60% of having the best data, is non-technical reminders. So we'll talk about why that I think was surprisingly effective in just a second. We find 0 effects, although we can rule out large effects of the kind of gender and race of the programmer, even when, for example, female programmers are trying to predict the math scores of women. They're not more accurate or more generous. And we find the same thing with regards to the IET results. These are basically unrelated to, there's no evidence, and we can rule out large effects of the IIT being sort of passed along into the code. And then finally, the technical advice seemed to make everything worse. And so this was true across lots of different outcome measures. Okay, so why is this? I think the most interesting thing is that the technical advice didn't work and the reminders did. And what we find is that the programmers who got the reminders implemented their own version of some sort of debiasing algorithm that may have not been at the technological frontier, but they intuitively understood. Whereas the people who got the technical advice tried to implement this. I'm not sure they completely understood what to do, even though we tried to make this as clear as possible. And I think most education tries to make this clear. They ended up either implementing it wrong or not doing it at all. And that's why this seems to have ended up backfiring. On the topic of the diversity and why it didn't seem like the more diverse programmers or the non-white, non-male, we do find evidence that they were more aware of the algorithmic bias issues, but this didn't end up being translated into their code or into the quality of their different predictions. So just to summarize, we find no evidence that minority programmers end up writing more socially aware code, but reminding about the group about bias does seem to have a positive effect. And it also seems like there's a trade-off between pushing frontier technology, that is this fair machine learning set of ideas aggressively, versus implementing something that the programmers can actually do, and that's better than the status quo, but isn't up to the frontier. Okay. So lastly, just a couple of meta lessons from the thing. If you're a personnel economist, AI engineers and tasks have a lot of really attractive measurement properties. You can see how hard they work. You can see how high quality their work was. You can measure the bias in various directions. And you can also manipulate them fairly easily by changing their data sets, their incentives and whatnot. They're arguably a more interesting subject population than, say, safe glass engineers, or sorry, safe glass, auto glass installers. The other meta lesson, I think, is that there's lots of hot air and discussion about biased AI, but this doesn't just have to be a theoretical sort of speculative topic. You can actually collect data and quantitatively measure and empirically measure what works and what doesn't on these biased AI topics. So that's all. Thank you very much.